Let us now take a look at our arc lengths and area of sectors in radian measure. But before we do that, let us do a quick recap on the angles in degrees versus the angles in radians. Now we know that 180 degree is essentially equals to pi radian. So if it is 90 degree, half of 180 degrees, we can expect that 90 degrees when converted into radian is essentially pi over 2 radian. Now, 45 degrees is then half of 90 degrees. Therefore, you can expect 45 degrees when converted to radian will be this pi over 4 radian. Now, we know that 60 degrees is actually 60 degrees is 1/3 of 180 degrees. So if I were to convert them into radian, it is as good as pi over 3 radian. Then if 30 degrees is half of 60 degrees, you can expect this to be pi over 6 radian for 30 degrees. One other special angle that we can talk about is 270 degrees. 270 degrees is in between 180 degrees and 360 degrees exactly. So if 180 degrees is pi, 360 degrees is 2 pi, you can expect your 270 degree therefore to be 1.5 or 1.5 pi radian, which we can write it as 3 pi over 2 radian in this case. Alright, some people ask, do I have to memorize the angles in radians? Well, we have done in the previous part of the chapter that we can do conversion on the spot as well, so long as you know that 180 degree is 1 pi radian. So now let's go to arc length and area of sector. Now in degree measure, alright, we know that length of arc is essentially the angle in the center out of 360 degrees times 2 pi r. Remembering that 2 pi r is circumference. Alright, and it's not surprising because length of arc is essentially a fraction of the circumference. Then comes the area of sector. We also learned earlier that x degree out of 360 degrees times pi r squared. Remembering that this formula here is actually the area of circle. Alright, area of sector is a portion out of the whole entire circle's area. Therefore, it is that proportion over there. Now, what about if it is in radian measure? Now, since we know that x degree out of 360 degree is like a proportion or a section, all right, then in radian, all right, theta, which is the angle in the center, out of 360, or 360 expressed in radian is 2 pi, all right, is the ratio or the proportion. So if I let, oops, that's ugly handwriting. Let me write this again. If I let S, all right, represent the arc length of a circle, I know length of arc, all right, out of the circumference essentially is dependent on the theta, the unknown angle, the section that I have out of 2 pi. So if I do a little manipulation on this, I will know that length of arc is as good as theta out of 2 pi, that section, that ratio, that proportion that we want, multiplied by circumference. And we know that circumference is 2 pi r. Alright, so if I do a little tidying of this formula, I can see that length of arc, which is represented by S, is essentially radius multiplied by the angle in the center in radian. Alright, then for area of sector, if I let A represent area of sector, alright, I will have area of sector over area of circle is as good as theta out of 2 pi as well, because a sector is a certain proportion, is a certain section of that area of circle that you have there. Then if I do my little bit of manipulation, I know area of sector is as good as theta over 2 pi multiplied by pi r squared. If I tidy the formula a little bit, I have pi at the top, pi at the bottom. I'm going to do a cancellation. What I have now is left with half times r squared times theta as my formula. What have I been doing the last 2-3 minutes? Essentially, I've actually done a conversion, or rather I've actually done a manipulation to show you that in order to calculate length of arc in radian, I can actually use the radian ratio, alright, and then use it to multiply with the circumference or multiply the area and come up with this formula for arc length and this formula for area, and I can use them when I have instead of being given the degree, the angle in degree, when given in radian, I can use these two formulas to solve instead. Alright, so I once again repeat, this is the formula in radian measure, while just now earlier, above it, we have the arc length and the area in degree. Alright, let us try to use the radian measure to actually do some calculation as seen in page 9. Now, first question. The following sector POQ has a radius of 9 cm and a perimeter of 25 cm. They want you to calculate angle POQ in radian. Alright, so the question requires you to leave your answer in radian. So let's use our radian formula to solve them. Now, I know that my length of arc is given as PQ. I have my radius 9 cm at OQ, and I have a perimeter given to me at 25 cm. Well, don't be tricked. By the diagram, a perimeter versus the radius there. The perimeter of this sector actually has two radius, here and here. Okay, so in order to calculate the arc length PQ, we know that the arc length PQ is actually 25 minus 9 minus 9, minus both radius. And that leaves me with 7. The formula for arc length, the radian formula for arc length, is actually r theta. Alright, so if I know that the arc length is 7, I know that this 7 is also the same as r theta, which means my r in this case is 9. My r is the 9, the radius, and then that unknown angle I have there. So angle POQ in this case, oops, not PQ, but POQ, is as good as 7 over 9 radian. Alright, you're given the arc length, or rather you're given the perimeter. You can find the arc length by taking away both radius here. Then from there, you know that the arc length is 7. The arc length is also represented by the formula r theta in radian mode. So therefore, I put in my radius, which is 9. And then when I do my multiplication, I will see that the angle in the center, angle POQ, is as good as 7 over 9 radian. Knowing the angle POQ now, alright, we can go find the area of sector POQ. Now, if you have your angle in radian, then you have to use the radian formula for area of sector to solve this. So in this case, area of sector POQ, area of sector is half r square theta. Half r square theta. So over here, when I fill in the information that I have, that's 9 square, and this is 7 over 9 radian. I do my calculation, I will get 31.5 cm squared. Exactly. Alright, done with this example. Let's go to another one where no diagram is given to you and other values are given to you instead of a perimeter. this time round. A sector with a radius of 6.3 has an area of 51.2 cm squared. They want you now this time to calculate its perimeter and correct your answer to 4 significant figures. Alright, if you need the sketch, it basically says that you have this pizza slice, that sector. Alright, my drawing is terrible. I'm sure you can do a better job than me. And then my radius is 6.3 cm. 6.3 cm. This entire thing has an area of 51.2 cm square. Question wants you to find perimeter of this slice. In order to find perimeter, you need to know the arc length. To know the arc length, you probably need to know the angle so that you can actually calculate them. Alright, so this is what we are going to do. We are first going to find what's the angle in the center. Alright, since I'm given the area, alright, let's use the area formula then. So if I were to go write this down, area of sector. Of course, you may ask me, must I use radian formula or must I use degree formula? You can use either one. Alright, but for the context of this question, I'm going to use the radian mode instead. So area of sector, I know it's half r squared theta. So I'm going to fill in whatever I have, which is 51.2 over here, half here, 6.3 square there, and then the radian, the angle in the center, and I'm going to put it as theta. Alright, so if I calculate, my theta is as good as 51.2 divided by my half times 6.3 times 6.3 there. And this will give me my angle, if exact, will be 5120 over 3969. Looks absurd, huh? But this is the exact value, so I'm just going to leave it as it is first since it's not my final answer anyway. Alright, therefore, to calculate perimeter of sector. Alright, to calculate the perimeter of this sector, I know perimeter is made up of 2 radius, so I'm going to take my 2 times 6.3, and I'm going to add the arc length. Since my angle that I calculated is in radian, alright, so I'm going to use the radian formula to solve. So the radian formula for arc length is r, which is 6.3, r theta, which is 5120 over 3969. Okay, go and do my calculation. I get a 20,229,315 in exact terms. But the question didn't want me to do in exact terms. The question wants me to leave my answer in 4 significant figures. So I'm going to get this sorted out. That's over here in conversion will be 20.7269, so on and so forth. 20.73 in 20.73 cm in 4 significant figures. We have done a little bit on area of sector. We've also done a little bit of arc length, done in radian mode. In the next video, we will do a little bit more with segment.